I have a video where I derived this. This is the acceleration vector in spherical coordinates. So it's not easy to do. I'll be honest with you. Okay, but I did it. And so I'm going to, but then once you have that acceleration in spherical coordinates, it's like, well, what are you going to do with it? And there are things you can do with it. But I want to do something that we could do both ways. Model a motion in Cartesian coordinates and spherical coordinates. And so what better to do than projectile motion? So what I'm going to do is do projectile motion using spherical coordinates. And you might think there's no reason for that, and you might be right. But I don't really care because I think it's going to be fun. It's going to be a lot of work. It's going to get messy. But that's just kind of, if we can get it to work, then that's just bonus. Okay. So let's talk about projectile motion first. So if I have projectile motion, if I have a ball moving through the air, and the only force acting on it is the gravitational force mg, that's going to be the mass times acceleration, and the masses cancel. So I get the acceleration is this gravitational field g, and then I can model the motion of that. I'm going to first do this in Cartesian coordinates because it's not too difficult to do. Yeah, I'm just kind of thinking out loud here. And actually, I'm going to do this in Cartesian coordinates in 3 dimensions and using a numerical model that I'm going to have to use later on. So I'm not going to do the best way, which would be an analytical solution because it's projectile motion. Anyone can do projectile motion, right? Instead, I'm going to use the Euler method. So I've already picked some initial values. So I have a ball launched at the position 5, 0, 0. So these are Cartesian coordinates. 5 in the x direction, 0, 0. The initial velocity, I just picked some values here, -2, 3, 7. And then the acceleration is in the negative z direction. So I put z as up just because I can use my normal x cross y is backwards. Let's see, no, this should be y, and that's x. That's my mistake. Wait, x cross y. No, it is right. This is x, and that's y. X cross y is z. I had it right the first time. And that way I can use my normal definition of the vector r in Cartesian coordinates. We have this whole problem with, translating between Cartesian and spherical coordinates. It can get really a bit of a problem. But let's just jump right into the numerical calculation in Cartesian coordinates. It's pretty easy if we do it this way. So if I have a equals, I'll just write it as 0, 0, negative g. Right, that's my acceleration. Now what I'm going to do, I'm not going to have constant accelerations in the r hat, theta hat, phi hat components. So I'm going to have to use a method like this. So I can say, if I break the time interval, the motion into small time steps, let's say 0.01 seconds, and maybe even smaller than that. During that time interval, I can assume that the acceleration is constant because it is. Okay, and say a equals delta v over delta t. That's how acceleration is defined. And if I say v2 is the velocity at the end of the time interval, v1 is the beginning. I'm going to go through this quick because I've done it a billion times. I feel like you don't want to see this. Then I can find, if I know the velocity at the beginning of the time interval, I can find the velocity at the end. v2 equals v1 plus a delta t. But I'm going to use the same method in spherical coordinates. And then I can assume that the velocity is constant during that time interval, which is not true. And I can say v is delta r over delta t. So that's the position vector. And I can get the same thing. R2 equals r1 plus v2 delta t. I like to write v2 because if I calculate this first, I'm using the velocity at the end of the time interval. And then I can say t equals t2 equals t1 plus delta t, and then just do the whole thing over and over again, and I should have projectile motion. So I already started a Python program to model this. I want to have 2 balls. I'm going to have one ball that moves with Cartesian coordinate calculations and one in spherical coordinates. So let's jump over here to the computer, and I'll jump back. So I've already started this messy code right here because I didn't leave any comments. So I wanted to make it like cool and hip. So I put a point for the origin. I put a the gravitational field vector. That's just I have this twice, right? Because I'm going to use g, the vector g, and I want to use the magnitude g in spherical coordinates. So I made two different variables. Then here's my ball. It starts at that same position. I gave it a radius and a color, big deal. A mass, which doesn't really matter. And then here's my initial velocity vector. And I wrote that as just as a constant because I'm going to use that later. And here's my initial position as just a constant again. L is just for drawing things. So then I have the ground. I made some arrows in the z-hat direction. And then if I run this, it doesn't run yet, but I mean, it doesn't move. You can see the z direction is that way, right? That way. And then there's my ball. So it's a little weird thinking about it in this terms, but there's my motion. Okay, let's model this now. So I put a time step of 0.001. So let's say while the ball's above the ground. So I can say while ball.pos, make this bigger. Ball.pos.z, remember where z is the vertical direction, is greater than or equal to 0, rate 1000. So rate tells Python, and I'm going to give you the code. Don't worry about that. Rate tells Python to don't do more than 1,000 calculations per second. And since I have a time step of 1/1000th of a second, this would run in real time if it's possible. Okay, so the first thing I'm going to do is to, I don't need to calculate the acceleration because I already have it as GV. So I'm just going to update the velocity of the ball. So ball, spell it right, ball.v equals ball.v plus gv times dt. So gv is a vector, right? Ball.v is a vector. This is a vector equation. This is one of the great things about WebVPython, which is what I'm using here, is that I can do these vector equations. I don't need to do an x, y, and z equation. I just do one. Now I'm going to update the position of the ball. So R for the ball, but the ball is also a object. It's a sphere, and its location is this POS equals vector 0, 0, 0. I'm going to change that value. So let's change the value. So ball.pos, that's my new position, is equal to the old position, which is ball.pos, plus ball.v times dt. And now I'm going to update time. I don't really need to. T equals t plus dt, and it should run. Should. Doesn't always mean it will. There we go. Projectile motion. Nothing super fancy. There's that. So that's my baseline, right? I want to do that in spherical coordinates. Okay, we got a bunch of work to do. So let's get to it. Let's go back to the paper. Okay, so here I am in the paper. What do I need to do? So I know this is true. And I also know from my previous video, link down below, watch it if you want to, look it up in a book, it doesn't matter. But the acceleration in spherical coordinates has these components. The r hat component is this. Now, reminder, just as a quick note, r double dot, if you haven't seen that, that's the second derivative of r with respect to t. And that's the r coordinate. That's not the r vector, right? That's the spherical r value. So there's my r component, r hat, the acceleration in the r direction, the acceleration in the theta direction, the acceleration in the phi direction. But what is the acceleration due? What is g in spherical coordinates? That's my problem, right? What is g in spherical coordinates? Because I know g is negative z hat. But I don't have Cartesian unit vectors here. I have spherical unit vectors. You know, and the reason that this becomes so complicated is because r hat, theta hat, and phi hat do change with time. As you move positions, these change. So the derivatives are a lot more complicated. So I need to get z hat in terms of Cartesian coordinates. That's my first step. Now, it's not trivial. So let's do this. Let's say I'm going to take x hat, y hat, z hat are Cartesian coordinates. I did find in this video, again, you got to watch that video, I found r hat, theta hat, and phi hat in terms of Cartesian coordinates. I'm going to skip some of the steps here, but what this gives me, it allows me to find these as I can build a matrix to find the unit vectors, because I have 3 equations. Okay, so let me write it down and then I'll tell you what I'm going to do. So I have this. I'm looking at my notes because I forget what it was. R hat, theta hat, phi hat as a vector equals the transformation matrix of, let me see, there it is. No. Yeah, this is it. I do have notes because I've made a mistake before. It's going to be equal to sine theta, cosine phi, sine theta, sine phi, cosine theta. Just a reminder, you can't just intuitively find this. You got to say, how does the vector r change with respect to the variable r, and then normalize it. That's what you do. And then I have cosine theta, cosine phi, cosine theta, sine phi, negative sine theta. And then finally I have negative sine phi, cosine phi, 0, times the vector x hat, y hat, z hat. So what this tells me is that if I want to find, let's say, the r hat vector, it's just going to be this row multiplied by that column. So it'll be sine theta, cosine phi, x hat, sine theta, sine phi, y hat, cosine theta, z hat. And that makes sense, right? Because that's just the unit vector anyway. But what I want to get is z hat in terms of these. So it turns out that this is a orthogonal matrix, and so if I want to take, I can take the inverse of this by just taking the transpose. So if I do that, then I get the following. I'm going to write it down because I actually did make a mistake here. So then I can, if I multiply this by the inverse and I multiply this by the inverse, then I can get this opposite. I can find x hat, y hat, z hat in terms of r hat, theta hat, phi hat. So let's do that. So I'm going to say x hat, y hat, z hat is going to be equal to, now just transpose this matrix. So that means I'm going to switch the diagonal columns, stay the same, and then I switch this with that, I switch that with that, switch that with that. So it's not too bad. So but I did make a mistake here. So I'm going to write it down. Oopsie, sine theta, cosine phi, cosine theta, cosine phi, negative sine theta, and then over here I have sine theta, sine phi, cosine theta, sine phi, cosine phi, and then the last row is cosine theta minus sine theta, 0, and this is going to be r hat, theta hat, phi hat. Now I don't need all the unit vectors because the acceleration just depends in the z direction. So which one of these would give me the z hat? It would be this row operated on that vector. So I can write z hat equals cosine theta r hat minus sine theta theta hat plus 0. And that's what I want. And you'll notice that it doesn't depend on phi. In our normal, see, if I have gravity pointing down that way, it doesn't have a component in the phi hat direction no matter what. But it does have a component in the theta hat and r hat direction. And you probably could have just used intuition to find this, but my intuition fails me so many times, I don't trust it. It's sort of like Luke Skywalker learning how to use a lightsaber, and Obi-Wan puts that blast shield down. Your senses can deceive you. Don't trust them. That was a Star Wars joke. Okay. So now I can say A is equal to negative g z hat. But I can convert this into spherical coordinates. So I can say A is going to be negative g cosine theta r hat plus g sine theta theta hat. Now I'm in business. Now I'm doing well. Okay. So with that, wait, do I have a minus? Oh, I already made a mistake. G, I have G as minus minus. Minus G. Let's see, Z hat. No, that's right. It should be plus. Okay. I'm pretty sure. I'm going to make a mistake. I can feel it. I don't want to make a mistake. So now let's take this acceleration and this acceleration. This is the acceleration in coordinate terms, and this is the acceleration in terms of, so let me just, I can write it over here, equals negative G cosine theta r hat plus G sine theta theta hat. This tells us something really important, right? Because now I know the r hat component of the acceleration has to be equal to this. The theta hat component of the acceleration has to be this. And this term has to be 0. So I actually get the following 3 equations. Where did I write those? I'm going to write those over here. Okay, so let's write those down. I'm going to run out of paper. I already see that. I'm going to have to get some more. Okay, so I have AR. The R component of the acceleration is negative G cosine theta. And that's going to be equal to this component. I like my paper straight. Okay. So that's going to be equal to r double dot minus r theta dot squared minus r phi dot squared sine squared theta. And then I can do the same thing, equals. A theta is going to be equal to plus G sine theta. I'm just trying to think if that makes sense. Yeah, that makes sense. Okay. And now I can relate that to the theta hat component of the acceleration, and I get 2 r dot theta dot plus r double dot theta minus r phi dot squared sine theta cosine theta. And then finally I can say a phi is equal to 0, and that's going to be equal to 2 r dot phi dot sine theta plus r phi double dot sine theta plus 2r theta dot phi dot cosine theta. Okay, so now I have 3 equations. And you'll notice what I want to do is to take this equation and solve for r double dot. This equation solve for theta double dot. This equation solve for phi double dot. So that gives me this one. It's pretty easy. Now I do have this term over here. So I get r double dot equals r theta dot squared plus r phi dot squared sine squared theta minus, because that was right over there, minus G cosine theta. That's important. So now I can calculate the r double dot acceleration at any point. And I need that. Okay, now I can take this one and solve for theta double dot. So if I move these terms to the other side and divide by r, I get theta double dot equals G over r sine theta. And then I have minus 2 r dot theta dot over r. And then I have plus phi dot squared sine theta cosine theta. The r canceled there. The sine theta canceled there. And then finally I can do the same thing for this phi double dot. I'm going to move these 2 terms to the other side and divide by r sine theta. And I get phi double dot equals negative 2 r dot phi dot over r minus 2 theta dot phi dot cosine theta over sine theta. So imagine these are differential equations, but they're not easy to solve. However, if I break this into small time intervals, then I can say r double dot equals delta r dot over delta t. I can say theta double dot equals delta theta dot over delta t, and phi double dot equals delta phi dot over delta t. And so I can use this to update r dot, so I can say r2 dot equals r1 dot plus r double dot delta t, theta 2 dot equals theta 1 dot plus theta 2, no, this is theta double dot delta t, and then phi 2 dot equals phi 1 dot plus phi double dot delta t. So I'm assuming, I'm using that same idea for the numerical calculation. I'm assuming that the time interval is small, and during this time interval r double dot's constant, which is not. But I can do this. Now, and then I can do the same thing. I can do the same thing for r, theta, and phi. I can say r2 equals r1 plus r2 dot delta t, theta 2 equals theta 1 plus theta 2 dot delta t, because I'm using this afterwards, that's why it's a 2. And then phi 2 equals phi 1 plus phi 2 dot delta t. Now there is a problem. The problem is that in order to do this calculation, and more importantly, in order to do this, if I want to find the r velocity at the beginning, at the end of the first time interval, I need the r velocity at the beginning of the first time interval. If I want to find theta velocity at the end of the time interval, I need theta dot at the beginning. So I need initial conditions. I need my initial conditions for r1, r dot 0, theta dot 0, and what was it called? And phi dot 0. This is a lot of math. Don't kid yourself. And I'm probably have made at least one mistake. But if I make two mistakes, two mistakes might make it right again. So I'm just hoping for that. Okay, so we need to get an expression. We need to find the initial r1, r2, and r1 dot, theta 1 dot, and phi 1 dot. So if we go back over here, I know my initial velocity, right? I wrote that down right here. So I can say this says x, I'll call it 0. x0 dot is equal, and that's the x coordinate, is -2. That's a line. y0 dot is going to be equal to 3, and z0 dot equals 7. But I also have x, y, and z in terms of my spherical coordinates, right? So if you look up here, I'm not going to redo it. I'm just going to, it's not a hard derivative. R equals r sine theta cosine phi x hat. That is my x component. That's my x component of the position. So I can find my initial x position. I can find r, sine, and theta pretty easily. If I take the derivative of this with respect to time, I'm going to have to take the derivative of a bunch of the stuff. But I can do it. And that's going to be my velocity in the x direction in terms of spherical coordinates. Okay, so let me just do this first one. If I take the derivative, I'm just going to write it out. If I take the derivative of this with respect to time, I get the following. Actually, I should do this on a new piece of paper. So x dot is going to be equal to, I'll write it out as d dt of r sine theta cosine phi x hat. That's it. Actually, that's x. That's all I need to do. Okay, but if I do that, I get the following. So I take the derivative of r. It's going to be r dot times the stuff sine theta cosine phi. But now I need to take the derivative of sine theta, which is going to be cosine theta. But then I need to take the derivative of the inside stuff. So I get, wait. I have a minus there. Cosine. Oh, I just did it back. Oh, I wrote it backwards. That's fine. I'm going to, I wrote it a sine theta, cosine theta. I'm not sure why I wrote it backwards. Okay, well, I'm going to write it in the order I did it before so I don't make a mistake. Minus r phi dot sine phi sine theta plus r theta dot cosine phi cosine theta. Now, we need to use our initial conditions, and I can actually solve for r dot, right? Because I know x dot is, what did I say it was? X dot's -2. Okay, now I also need to get my coordinates. So if I go back over here to, I should have written it over here. Right here. So there's my initial position. Okay, so I picked an initial value. So R0 is going to be equal to 5, right? Because the magnitude. I can also, if it's on the x-axis, which it is, then theta 0 is equal to pi over 2, right? Because that goes all the way down there. And phi 0 is equal to 0. So if I use those values for r, so -2, r dot I'm trying to solve for, sine of theta is equal to pi over 2, so that is equal to 1. Cosine of 0 is 1. So I get -2 equals r dot times 1. And then here I have sine of phi, but phi is 0, so that's 0. And then here I have cosine of pi over 2, so that's 0. Yeah, so I just get that. Okay, so now let's do the same thing using my derivative of y. So I know that y dot velocity is 7. So y dot equals 7. And that's going to be equal to the derivative of the y value, which is r sine theta sine phi. So if I take the derivative of that, I get r dot sine phi sine theta plus r phi dot cosine phi sine theta plus r theta dot sine phi cosine theta. Now again, at t equals 0, at the initial conditions, here I have phi is 0, so this term is 0. Here I have, phi was, if phi is 0, so that term is 0. This is 0 too, because theta is, no, phi is, well, let's see. No, that's all right. Okay, this term is 0. This term is not 0. This is going to be r times phi dot times 1 times 1. So r is 5, so this is going to be equal to 5 phi dot. And then that term is 0 because cosine of theta is 1, but sine of 0 is 0. So that term's 0. So this is equal to 7. So phi dot is equal to 7/5. Okay, now we need to do one more. Z dot equals, what was it, 3? And that's going to be equal to the derivative with respect to time. This one's actually easier, of r cosine theta. And that's going to be equal to r dot cosine theta minus r theta dot sine theta. And if I put in at theta equals 0, then what do I get? At theta, at time t equals 0, theta is pi over 2, so this term's 0. This term is 1, and so I get 3 equals -r, which is 5, times theta dot. So theta dot is going to be -3/5. Okay, so I have everything I need. I think I can go ahead and start plugging stuff in. Okay, because what I'm going to do, like I said, back over here, remember what we're doing. I'm going to just model the motion. I'm going to, every time interval, I'm going to take the initial values and find the new values, just like I did before. Take the initial velocities, find the new velocities. Using these, the first thing I'm going to do in the loop is to calculate r double dot, theta double dot, phi double dot, use those to update the velocity, use the velocity to update the position. We've got some work to do, so let's get to it in Python. This might be my longest video yet. Maybe. Who knows? Okay. So let's go up here. We've already got that all working. Let's make another ball. So I'm going to call this one ball 2. And it's going to be a sphere. and it's going to be in the same position. So let's say position equals ball. So what did I do? Yeah, same position. I'm gonna make it cyan. Ball.pos. This has the same position. Actually, let's just write it out because sometimes weird things happen when you do that. Vector 5, 0, 0, same starting position. Same radius. Radius equals 0.01. 0.1. Let's make this a different color. Color equals color.cyan. And then make trail equals true, then it'll leave a trail. Okay, the next thing I need to do is to write down my initial. I have all these variables, right? I have all these variables I want to write. So I'm going to say RS. I can't use. Did I use R? I don't think I have R anywhere. Okay, I can say R. R is my spherical coordinate value, and that is going to be equal to just 5, right? We already said that. Theta is equal to pi over 2. Phi is equal to 0. And these are the initial values because I'm putting them at the beginning, right? There's my initial values. Now I need R dot. So R dot is going to be equal to, I'm just going to write it out. I said it was what? -2? Yeah. -2. Theta dot is going to be equal to -3/5. And phi dot is equal to 7/5. So that's what I need. Okay. Now I'm going to go down to my loop, and I've already done the position updates for my Cartesian ball. I need to first calculate R double dot. And so R double dot doesn't have a value before it. I can just do it once, right? So R double dot, DD dot. And if I'm now looking at my equation over here where I calculated R double dot in terms of theta and G and all that other stuff. So it's going to be, I'm just looking at my equation. It's going to be R times theta dot squared plus R times phi dot squared times sine of theta squared minus G times cosine theta. Now I'm going to calculate theta double dot. Theta d dot equals G over R, I'm just going to write it the way I like it, times sine of theta. I'm going to have an error. You know I'm going to have an error. Minus 2 times R dot, right? Now that R dot, I've already defined it, so there is a value for R dot. R dot times theta dot. If this works without an error, I'm going to freak out. Divided by R plus phi dot squared times sine of theta times cosine of theta. Now I need to calculate phi double dot. Phi d dot equals -2 times R dot times phi dot divided by R minus 2 times theta dot times phi dot times cosine theta divided by sine theta. Okay, so now I have my double dots. I can use those to update my dots, right? So now I can say R dot equals R dot plus R double dot times dt. Theta dot equals theta dot plus theta dot double dot times dt. And then phi dot equals phi dot plus phi double dot, that's where I almost made a mistake, dt. Now once I have those, I can update my actual positions. R equals R plus R dot times et. Theta equals theta plus theta dot times et. And then phi equals phi plus phi dot times et. Now I do have another thing I have to do. I have to update the position of my ball, right? 'Cause I just calculate the variables. I need to switch this back into Cartesian coordinates. WebVPython uses Cartesian coordinates. So I'm going to do this. Ball to, what did I call it? Did I call it ball2? Yeah, ball2. Ball2.pos equals vector. The x component, now I'm just writing out my r in vector coordinates, Cartesian coordinates. So it's going to be r times sine theta times cosine phi. That's my x coordinate. My y coordinate is going to be r times sine theta times sine phi. And then my z coordinate is going to be r times cosine theta. Whew. Okay. Let's see if this thing actually works. I don't really know that it will, but you know, what are you going to do if it doesn't work? What are you going to do? I actually do know something. This is not what I wanted to do. Okay, let's see. Okay, let's run it. Okay, so it worked, but it didn't do the same thing. So I have an error. I'm very confident in my work, okay, but I'm surely I made a typo. So I actually did work this out beforehand. I'm gonna copy what I had and see if it works, because I do want to do that. Let's see, theta double dot. Okay, there is one change I need to make. So all this stuff. All this stuff up to here. I'm going to replace it with that. Oh, I missed the r dot. And then in my other calculation, I had rs instead of r. So I need to get rid of these r's. I don't know why I called it rs. R, 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 R. You gotta say it every time or it won't work. R, R, R. Okay, now if I run this. Please work. I don't want to. No, it didn't work. It's still the same thing. Okay, well, let me switch over to the version that does work. I'll give you both versions. Like I said, I promise you this works. Where'd it go? Oh, there it is. Okay. Okay, so this one does work. I don't know what my error was, and I can't make this video so much longer. It took me long enough time. I made an error finding the initial velocity. But those are the two balls right on top of each other, and that's really good. But that's not what I want to do. What I want to do is to make a plot of r versus time, theta versus time, and phi versus time, because that will be the most fun. So up here, I'm going to make a graph. So say G1, let's call it GR equals graph X title equals T, Y title equals R. I'm not going to put units. Width equals 400, height equals 100. Okay, and now I'm going to create an R plot. So let's say FR equals G curve, color equals color.blue. Okay, now I'm going to copy all that and make another graph. And this one's going to be theta. And let's call this GT for theta T. And let's make this one red. And then we'll make a phi one. We'll call that a GP for phi. And this will be phi. And this will be P. And this will, let's just leave this as black. Okay, so now down here, I'm going to plot those values. So FR.plot TR. FT.plot T theta. And then FP.plot T phi. Let's see if that works. Something didn't happen. Can't find variable r. Oh, I called this one rs. Forgot I switched programs. There we go. Okay, so you'll notice here the really interesting thing, phi is just straight, right? Because there's no acceleration in the phi direction, so the phi position changes constant with time. It's constant velocity. But that's not true for theta and r. And r, you can think about as you shoot that, it actually comes closer and then further away, then closer again, based on the position, because you're measuring not just how far away it is in the xy plane, but also in the z direction. So that's kind of cool. Let me just say this. What would you use this for? What if I wanted to build like a baseball tracker, right? And it's a projectile motion in the air, and I need to follow both theta and phi as a function of time. Well, there's your theta as a function of time right there. So that's kind of cool. I feel really bad that I made a couple mistakes, but this is a pretty hard problem. And I am happy at the end that it worked. I'm going to give you both versions of the code. If you want to figure out what's going on, you can. But I hope that helps. And don't forget, if you want to see how do you find the acceleration in spherical coordinates, that's another video.